Welcome to the live stream from the Keck Observatory, where we're offering a rare glimpse into astronomical research and observing run, where we're studying the center of our Milky Way galaxy. The image you're looking at is of the Milky Way and taken somewhere here on the Big Island, it looks like, and you can see towards the center of the galaxy the Milky Way as it's aptly named. My name is Randy Campbell, and I'm on staff here at the observatory, and I'll be your host for this evening. And tonight's observing team is from the University of California, Los Angeles, UCLA, where the team is led by the principal investigator, Professor Andrea Ghez. Her now and bring her into the video. Hi, Andrea.
Hi.
So, maybe you can tell us a little bit about the science program and what we're going to be doing here observing tonight, and introduce some of your team as well.
Well, tonight we're looking at the center of the galaxy, and in particular the black hole at the center of the galaxy. And we've been carrying out this program at Keck Observatory for the last 20 years, doing a whole bunch of things that we're going to talk about shortly. But before I get going, let's...
Let me explain a little bit first. We're at the headquarters facility here at Keck Observatory. Of course, it is not the same location as the telescope. The telescope is on the summit of Mauna Kea here on the Big Island of Hawaii, which is a nearly 14,000-foot dormant volcano, where two twin 10-meter telescopes exist that are part of the Keck telescopes. We're in the Keck 2 observing room here at headquarters, and we're doing the observations remotely from headquarters, and we have a video link to Jason McElroy, who's on the summit, and you can see that video link over there. Say hi, Jason.
Hello.
Yeah, that's Jason. He's an expert in the operation of the telescope and a lot of the subsystems. He's on the summit, making sure everything goes well there. And then we have a bunch of screens down here at our headquarters where we're operating some of the instruments and planning the observations and carrying them out. So I'll get back to the introductions now from Andrea, her observing team.
Okay, let's look at reasonable space.
So we're here with a group of people from UCLA, my team. At the controls here behind us, you can see Brianne Satarsky, who's a graduate student at UCLA.
Hi.
So she's running the camera, which we're using to take pictures of the galaxy. In fact, tonight we are on both telescopes. So we have, our team is actually split between the two control rooms. So we'll be bringing people in as we move back and forth.
Okay, and I also want to introduce Luca Rizzi. He's also one of the staff astronomers here at Keck. And Luca is an expert in both the instrument and the adaptive optics system, which we'll talk about more, but just wanted to introduce. It takes a whole team of experts to make an observing run like this happen. So we wanted to give you a flavor of how many people are involved. All right, so it's a fairly large group. The Galactic Center study is one of our premier programs here at Keck. So we thought we'd offer you this rare glimpse into how an observing run takes place, and then we can also talk about some of the science and some of the results, which we'll go into. So I guess the first question I'd like to ask Andrea is, why study the Galactic Center? I mean, the galaxy, the Milky Way is a pretty big place. You can study any portion of it. Why the center? What is the center? And tell us a little bit about that.
So we're studying the center of the Milky Way this evening because there is a supermassive black hole that's located there. This gives us an opportunity to understand both the physics of black holes. We're interested in testing some ideas about general relativity that we can do uniquely around the black hole. And we can also look at or try to understand what role black holes play in the formation and evolution of galaxies.
So not just our Milky Way galaxies, but all the extragalactic work. This work can extend to knowing about other galaxies as well. So.
Our galaxies, because our galaxy center is the closest example of a galaxy center that we'll ever have to study, this gives us a great opportunity to study in much finer detail what goes on at the center of a galaxy here in our own backyard, and we can apply that to other galaxies.
And the Keck telescope is a good instrument to use for doing this work. Is that true?
The Keck telescope is a fantastic facility to use. I feel very, 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 very privileged to be able to do my research here. In fact, I like to tell my students at UCLA, Keck is why I wanted to work at UCLA, and it's why I stay there. And having access it's just a very big privilege.
So what are the properties of this particular telescope and instrument and things? I mean, it's a 10-meter telescope that's made out of 36 hexagonal segments. And so that diameter makes it have a large primary mirror, which gives you a lot of collecting power. So you have good sensitivity. You can see things that are faint. What else does
So large telescopes offer two advantages. One is, as Ruth just said, is the ability to collect a lot of light, to see things that are very faint, which corresponds to things that are very far away. But the second thing that large telescopes offer is the ability to see very, very, very fine detail. And that's the capability that I've been interested in. And it's the capability that actually has been much harder to achieve. It turns out having a telescope act like a light bucket is fairly straightforward, but achieving finest resolution is much harder.
Sharp is a challenge. We're down here at headquarters, and we're working with digital imaging, and we're not at the telescope, and we're not looking through an eyepiece or anything like that. We have specialized instruments that connect to the telescope, and you're using an instrument that is called NIRC-2, which stands for Near Infrared Camera Generation 2, the second one was built. And it's sensitive to light infrared. And maybe you could talk a little bit about some of the challenges of observing the galactic center. One of the first images we showed the beautiful Milky Way, but you see dark and light bands in that Milky Way. And the center dark. Explain that a little bit. And we can pull up another image to help highlight.
Well, we could. There's actually a couple of interesting things that we've already mentioned that might be worth going into in a little bit more detail. The way let's start with the infrared piece.
You should never feel afraid to approximate.
All the data that we collect is in the infrared, and that's important because the infrared allows us to see through the tremendous amount of dust that is in the plane of the galaxy. So we live in the Milky Way, which is a flattened disk-like structure. So when we look up at the night sky, when we see that band of light that we showed in the first image.
Let me bring that
up again.
Let's do that.
Oh, shoot. That's weird.
So in this image, which is what you can see from Hawaii when you look up at night, you see the band of the Milky Way. This is the galaxy, and the light that we see in this image comes from all the starlight. But you'll notice that in the center of that plane, there's a dark line. There's a lack of light, and that comes from all the dust that is also in the plane of the galaxy. And dust is like smog in Los Angeles. It's very good at absorbing the light that our eye detects. But if you observe at wavelengths that are not in the optical, which is what our eye detects, but rather in the infrared, which is just longward of what your eye detects, so at wavelengths where your TV remote control work, the wavelength is longer and can penetrate all the dust that's in the plane of the galaxy. So in fact, maybe we can show you.
Yeah, we've got a switch a visible wavelength picture similar to what Hubble telescope or some other visible imager might take. Just a few stars, but then when it switches to infrared, you see many other sources of light that pierce through the dust and are picked up in the infrared picture. There's also some stuff going on with you. Maybe we could peek in. Tonight's a little bit of a challenge for observing because the weather isn't ideal. There's some clouds up there, and so the observer on the summit is advising Brienne on what to try and get some observations done through those clouds. That's the chatter you hear in the background. We'll go back to the science a little bit.
It's basically just I just pull it.
So getting back now to this question of the sharpness of the image, the infrared image we showed you earlier is limited in sharpness by the fact that the atmosphere is blurring out the image, and so even though you see a lot of sources, they're all kind of crowded together and kind of looks a little bit blurry. So we have another technology here at the observatory that is called adaptive optics. And adaptive optics is a technique for canceling out the blurring effects of the atmosphere, sort of like noise canceling headphones for your telescope. And we have a demonstration of that here in one of the slides, but we'll bring that up here in a minute. But so the way that adaptive optics works is if you have a sample of a bright star and you know what the atmosphere has done to that bright star, you can sample the blurring effects and you can cancel it out with what's called a deformable mirror, or a mirror that again just sharpest image possible. And for some programs that's critical, like this program. And let me see, I'll bring up this demonstration for you. It's this one. Maybe Andrea, you can talk about why adaptive optics is important to your program.
So in the work that we're doing, we're interested in seeing the stars that are as close as possible to the center of the galaxy. And one of the challenges is the blurring effects of the Earth's atmosphere. The way I like to think about the blurring effects of the Earth's atmosphere is the problem of the atmosphere is like looking at stones on the bottom of a moving river, and the river is continually blurring our vision of the stones. So our job with adaptive optics is to still the moving river of the atmosphere. So once we do that, we can see the center of the galaxy. We're trying to bring up another little animation that shows how this works. But once we can see these stars, in our original work, or when we got going with this work, our objective was to prove that a supermassive black hole exists at the center of the galaxy. So we wanted to watch how these stars move.
Yeah, I want to ask you. Okay, here comes our demonstration of before and after with adaptive optics. So as you can see, you start off with a relatively blurry image, and then you sharpen it up by about a factor of 10. In other words, each of those stars gets smaller by a factor of 10, and then it reveals many individual point sources in this region of the sky. So a pretty dramatic demonstration, and without it, you couldn't. The region that the box is drawn around, without it, all you see is one big sort of source of light, and then once you sharpen that up, then there are many sources in there that you can track individually. Yeah, so I wanted to ask you about a black hole. When was it first sort of theorized that there might be a black hole at the center? Is it you're looking at other galaxies and their rotations, and somewhere along the line we thought, well, there must be something like that at the center of our galaxy, and then
Well, the original idea for supermassive black holes at the center of galaxies came from observations of a small subset of all galaxies, which are much more active than our own galaxies. They're called active galactic nuclei, and these galaxies emit tremendous amounts of energy from their cores, and that led people to suggest that, well, maybe there's a powerful engine like a supermassive black hole. And it was only in the 1970s when Lyndon Bell and Rees in England suggested that maybe our galaxy, which is an ordinary, completely garden variety, nothing special about us, galaxy might have a supermassive black hole. And the idea there is that maybe all galaxies have supermassive black holes, and that the majority of them are just invisible because there's nothing feeding into them, and that the active galactic ones are the special ones that are feeding on their environment.
so there's not this same sort of activity at the nucleus of our galaxy.
Right, our galaxy is completely quiet.
Right.
So our black hole is a very mild-mannered beast.
So how do you go about finding a black hole if it's mild and not active? But now you have this technique where you can see through the dust, you can sharpen up, you can see all these little sources of light near this center. And why? How did you know that this was the region to look? Also, why not look somewhere else?
Let's see. So lots of questions there.
Yeah.
The way you show that there's a supermassive black hole is you watch how stars orbit the region at the center of the galaxy. And the idea here is that these stars will move under the gravitational influence of the black hole. And so we're about to show you an animation that shows how the stars that have been cleaned up in this first animation have moved over the last 20 years. And through the orbits of these stars, you can measure how much mass is inside their orbit. And these stars, and in particular, the star that's being traced by a yellow line, the name of this star is SO2, goes around the center of the galaxy every 16 years, shows that there's 4 million times the mass of the sun inside a region that corresponds to the size of our solar system. So it's a tremendous amount of mass inside a very small volume, which is the proof of a black hole. And you can only do that with the ability to correct the atmosphere, because otherwise this whole region would be just one big blur. So the development of adaptive optics and earlier versions of adaptive optics is key for this experiment.
I see. So you can measure the mass directly by measuring the gravitational effects that it has on the orbits of these stars. And you can also constrain the size of whatever this large source of gravity is, or not so much? Or?
Well, the orbit tells you how the region that you can find that mass to. So the closest approach of SO2 is about the size of the solar system, or 100 astronomical units.
Okay.
And that's all you know. You know that the 4 million times the mass of the sun is inside that small region.
So it's dark, it's compact, and it's supermassive, and therefore it proves
Must be a black hole.
Must be a black hole, yeah. Looks like a black hole, smells like a black hole.
And
Okay.
so you've asked actually a couple of other questions about how did we know where to look.
Right.
You have to define where you think the center of the galaxy is. And so the first thing you can look at is where, at the center of the galaxy, the density of stars increases as you go to the center. So that's one way to determine where to look. But the second piece of this was actually that at the center of the galaxy, there was a somewhat unusual radio source that people had already identified. Its name was Sagittarius A star. And people wondered whether or not this was a very faint equivalent of the active galactic nuclei that we were talking about earlier. So we looked. So when we started our work, what we targeted was that the location of that really unusual radio source. And what we discovered is that where these orbits X marks the spot for the black hole. In other words, you can figure out where the focus of that orbit is. And that is where you think the black hole is exactly where that unusual radio source is. So that both tells us that there's a black hole and that that radio source is associated with the black hole.
So, so you've been studying this environment at the center of the galaxy for many years, and obviously the supermassive black hole confirmation is one major result. What other sorts of outcomes and scientific results have you come up with by studying this region? One thing I'm curious about is, how far away from Earth is the center of our galaxy? Is that something you're able to give a measurement of?
Sure. The center of our galaxy is 8,000 parsecs or 26,000 light years from Earth. So if we measure distance by how far light will get in a year, we can talk about light years.
Uh-huh.
So that's how far this black hole is. And in fact, our measurements of the orbits, not only with images, but also with the spectroscopy, gives us a direct measurement of the distance to the black hole, which is a key parameter for understanding the structure of our galaxy. So it's one of those fundamental parameters that help us understand the structure of the galaxy, what the shape of the dark matter halo might be, and it ultimately, if you can determine it precisely enough, can go into the determination of this of the cosmic distance ladder, which is key for understanding the largest scales of our universe. So that's one of the motivations that we have for continuing this work, which is a very precise measurement of the distance from us to the center of the galaxy. That's just one of the many, many reasons why we continue to go forward.
So, so nailing down these fundamental parameters, mass, distance, size, is what you're able to do with these very precise measurements with the Keck telescope, adaptive optics, and the infrared, and the special instrument there too. Is that a fair summary?
Absolutely.
Okay.
There are many things that we've already been able to nail down. One is the existence of the black hole, the mass of the black hole, the distance we've been able to nail down very precisely. And of course, we'd like to do so more, even more so. And what the future holds is our desire to test general relativity on both a scale, both in mass and proximity to an event horizon that's never been tested before. And that's all about nailing down this orbit even more precisely. And in particular, doing so during the next closest approach of SO2. So perhaps you noticed in that orbit, or in the animation, that the speed of SO2 is not constant. But as it goes through closest approach, it goes more quickly. So we're actually thinking about maybe bringing that back up.
You want to bring that back up?
Sure.
Okay. And so, general relativity. That's Einstein's theory of general relativity, and that hasn't been proven. It's not just accepted and as fact, or there's some tests of the theory.
There are. And in fact, it's rather remarkable. I mean, there are only 4 fundamental forces, and yet gravity is being one of the 4 is actually the least tested of all of these in the form of general relativity. And so there are some tests, but not on all scales, or both in terms of spatial scale or mass scales. So if we can see the effects of general relativity on a star like SO2 as it goes through closest approach, so we're just starting this animation again where it's at furthest approach, and you might notice that as it gets closer to the black hole, when it goes through closest approach, it increases its speed.
So with the Earth goes around the sun in an orbit that's governed by just normal non-relativistic effects. That it's well understood since the days of, of Kepler and Newton and the laws of gravity that they developed. So what's different about this orbit that you could measure that would be relativistic in terms of general relativity? Would the acceleration be different than what it would be with a normal Keplerian orbit then?
Yeah, it would be different, and in fact, the differences would be more exaggerated the closer you get to the black hole. You can think of this as space-time is curved near the black hole, and it gets more curved as you get closer and closer to the black hole. So out at furthest approach, we wouldn't see the difference, but as it goes through closest approach, and as our ability to make these measurements has improved. So in fact, while we have already seen a complete orbit, the technology that we've used has improved so radically that during the first closest approach, we simply didn't have the ability to see these effects. And now the next time around, we should be in a position to make those measurements. We know exactly when it's going to happen. It's going to happen in 2018. And you need to nail down the orbit well enough, in other words, to understand the classical orbit as in how the Earth goes around the Sun well enough such that you can see the deviations in 2018. So that's one of the things that we're doing during this run.
So even though the current technology has given you the capability to nail down these fundamental parameters that we've already discussed, in order to test general relativity, you still need to improve a little bit your precision of your measurements.
And maybe we can give folks a chance to see actually the improvement. Maybe if we look at some of our earliest data, I actually love these early data sets. It's like looking at videos of your childhood. They were the best technology at the time, but today when we look back at them, they look a little antiquated. So
this one looks like it's got a problem.
It didn't transfer perfectly, so there's some flashing of bad pixels, which aren't actually in this animation. This is actually real data that shows one image from every year that we took of the first decade of our experiments, from 1995 to 2005.
Do I see SO2 there? The one that's we looked in the other one that's rotating clockwise near the center, the brightest one. Yeah.
That is indeed SO2.
Yeah.
I like to say that's my favorite star in the universe. And you can see it's whipping around, but you can see it, and it's what allowed us to figure out that there's a black hole. But in fact, today we can do so much better than this. This was a pre-adaptive optics measurement using a technique called speckle imaging.
This is similar data, but now it's colorized and smoothed out a little bit. Is that right?
So you know it's better technology because it's in color. This is with adaptive optics, same field, but more recent data. And you can see SO2 at the top of just rocking back and forth. We're just going through the time sequence forward and backwards. And you can see about a factor of 10 more stars. You can see things that are much fainter. And for the first time, we can see spectra. And spectra are really important in this work because not only can you determine the velocity along the line of sight, so the images allow you to see how things move in the plane of the sky, but spectra allow you to see how things are moving towards and away from you. So you get the third dimension of motion. And for the first time, you get to figure out what kind of stars these are. And there have been many, many surprises in looking at the spectra of these stars.
Is that right? Yeah. Maybe. Yeah. Let's hold that thought and come back in a second. I wanted to show a picture. So we're talking about the technology a little bit. Let's go back to the technology, talk about that, and then come back to the science again.
Okay.
So I mentioned we're using adaptive optics, and that you need a bright star in order to measure the wavefront error and then cancel it out. But unfortunately, as we mentioned, especially in this region where the dust is obscuring all the visible light from the bright stars, we don't have any bright stars. Or we the bright stars that are available are not optimum for use for this technique. So we have a way of getting around that by creating a laser guide star, a so-called laser guide star. And here's a fairly dramatic picture of the two Keck telescopes when they're studying the center of the galaxy and aiming the laser up there. And by using these laser spots, we can then create an artificial star, and then the adaptive optics technique works. And I think that has also made an improvement in the Galactic Center measurements.
Oh, it's been a huge improvement, and we've been able to learn so much more about the center of the galaxy. And in fact, I don't know if it's worth maybe showing a little bit more of the observations that are
Sure.
actually happening behind us, because these are the actual images that are being taken today. We've just looked at some of the historical data on the center of the galaxy, but what Brian is taking up is basically this year's version of this data. Let's see. There's a couple of different things that you might be able to see about what we can see.
Hi,
here.
Brianna.
So
So tell us what you're seeing over there, Brianna.
So this is the very heart of the galaxy, right where this...
You might not be able to hear Brianna, so I'll echo what she's saying.
So we're looking at the very heart of the galaxy.
Looking at the heart of the galaxy, the Galactic Center.
And right here is actually where the iron emission from the supermassive black hole is.
The
Right
which-
now it's in a quiet state.
She's pointing at the black hole at the center, where it would be, and it's not emitting any light right now, so it's very quiet. And these are live images coming onto her screen as she's taking them. And over to her left is the video conferencing unit that we use to communicate with the operator on the summit. So Brianne's talking to him to coordinate the observations. And then, as we introduced earlier, Luca Rizzi, the support astronomer tonight, is making sure that all the rest of the technology with the adaptive optics and the instrument is going well. And so that whole team. And we didn't introduce Mark earlier. Maybe we should introduce another member of the science team, Mark Morris, who's been one of the original ones. Hi, Mark. You want to come over here and talk a little bit about?
Hi, Randy.
Yeah. So we've talked about some of the fundamental parameters that have been measured and some of that. And I know one of the things you're interested in is the variability of the Galactic Center, and you study it at multiple wavelengths with lots of different telescopes.
That's right. We study with X-rays, with radio,
The mics, right?
radio telescopes,
Yeah.
and here we do, of course, with the infrared. And one of the interesting questions is, do they all vary in concert with each other at all these different wavelengths? And to some extent, they do seem to.
Uh-huh.
But we're trying to figure out what it means when some event occurs around the black hole. It leads to a flaring up of the emission of infrared wavelengths, and we can see that. And but sometimes it's also flaring up dramatically in the X-rays, and the only way we can observe that is using the orbiting NASA observatory, the Chandra X-ray observatory.
Because the X-rays don't get through the Earth's atmosphere, so you have to have a satellite telescope out in space in order to see the X-ray things. So we mentioned earlier that we're using both telescopes simultaneously tonight, and in the past couple of years you've been doing that experiment, so you could use the two Kecks and do the same, almost the same kind of experiment with two different wavelengths at Keck. Is that right?
That's right,
Yeah.
and we've done that, and,
Yeah.
it's they follow each other very closely at the different infrared wavelengths that we've tried it at. The question we were trying to investigate is there a delay between the two wavelengths that would tell us something about what is producing this infrared emission? We think we basically know what's producing it. It's the material falling into the black hole. But what's in detail, what's the mechanism that causes it to emit so much radiation? That we don't know.
I see. Yeah, that's fascinating. Um, and so on the other telescope tonight, we're using an instrument called OSIRIS, which is a spectrometer, and it also has a laser guide star system, and we're observing it simultaneous. We're observing the so-called Sagittarius A star, which is the official name of the Galactic Center because of the radio source. But we're doing simultaneous observations tonight with two lasers, and trying to get the most out of the power of the twin telescopes simultaneously. Um, so so there's so much going on, variability of stuff falling into the center of the black hole you're able to study. We've got all these fundamental parameters, and then we were also going to talk some more about the spectra that you're acquiring on Tech One and some of the things some surprises that you found in studying. You want to talk about that a little bit,
Sure.
Andrea?
Well, one of the things that we got interested in very early on as we took the first spectra was looking at what kind of stars exist there. And there are a couple of predictions about what you should see. And very simply, the expectation was that we should see tons of old stars and very few young stars. And
Why did you expect that? Why old stars?
old stars? Our
Yeah.
old stars have had plenty of time. They've been around the block a couple of times. They've had plenty of times to interact, and the prediction is those interactions should, over time, have those stars
Migrate towards the center.
migrate
yeah.
towards the center.
Yeah.
So you should see an intense concentration of these stars that are older.
So what did you find about the age then?
Well, let's first also talk about the young stars. The young stars, to get stars to form, you have a big ball of gas and dust, which is a very fragile thing. You want it to collapse under its own self-gravity. And yet, if you put it near a black holes have very strong tidal forces, and tidal forces tend to pull things apart. So for that reason, we didn't expect very many young stars. And yet, when we looked at the center of the galaxy with spectra behind adaptive optics, spectroscopy behind adaptive optics, what we saw was the exact opposite. Lots of young stars and very few old stars. So we had two mysteries on our hands, which is the fun of doing research.
So how'd they get there? Do we know?
We don't really know, but one important clue has come from, or at least the young stars, has come from studying the orbits of the young stars. And one of the things that has emerged over time, and the reason that over time has been important, is that while you can measure the orbits of the stars that are closest to the black hole relatively easily, because they go around much more quickly, as you move further and further away from the black hole, those orbits are much, much longer. So you need much more patience or much better measurements to actually see, to figure out how they're moving. But with patience, what we've seen is that many of the young stars are orbiting in a common plane. In fact, maybe we have an animation here that will show that nicely. We have a three-dimensional video.
The 3D one?
And the 3D
Okay.
video. That, it's an animation that shows how things have moved, but it pulls back and shows it in three dimensions, the three dimensions that we have for both the images and the spectra. In this video, things are color-coded. So the old stars are coded as red, and the young stars are coded as the green-blue. And when we pull far enough back, what will become evident is that many of these orbits are all in the same plane, very much like the planets going around the sun. And today we think that the way these young stars formed was very analogous. That they formed from a disk of gas and dust that was orbiting the black hole roughly a few million years ago to form this.
So
stars.
it'd have to be far enough. The disk would have to be far enough away from the black hole for these tidal forces not to tear apart the formation of the star.
Well, the key here is that in the disk, the density of the gas would be much higher than the density of gas that we see at the center of the galaxy today. So it's the density that allows the gas to overcome the tidal forces from the black hole. So that's the current thinking. Although there's been a lot of other ideas that have been posited to explain these young stars. But this is, I think, today our best guess at how the young stars got there. Is that they were actually formed there, but the conditions were radically different at the time of their formation.
This is really non-standard star formation because this environment is so hostile. You have the black hole. When you have enough gas there to form stars, they're also feeding the black hole copiously, and that puts out a tremendous amount of energy, far more than we're seeing now. And that must happen at various times. So several million years ago, when the stars were forming, the black hole itself was probably belting out a tremendous amount of energy. That might have helped form the stars because it creates a very high pressure which squeezes the gas clouds.
So the environment might have been similar to one of the active galactic nuclei in some other galaxies that we're able to study that Andrea was referring to earlier when this was going on. But, in other words, it would have been a very active environment. Very, very unlike the way it is today, which is basically quiet and not a lot of activity going on right at the center. But these stars are. Do you have an estimate of how old they are then? What's young? What's the young star?
These young stars are just a few million years old.
A few million years old. An
And
old star would be
a billion years old.
A billion or older.
Yeah.
And so, in that sort of time frame, though, that formation must have been relatively recently in the history of the galaxy. Not too long ago, we had an active galactic nucleus, and but right now it's a million years later. We've got these young stars orbiting around, and that were the formation of that, and then all the gas and stuff got blown out, and now it's quiet. I guess something like that.
And it may cycle back around and happen again, 10 million years or 20 billion years from now.
Right. Now there's some gas in that in the region, and you see evidence of that in your images and spectroscopy.
Absolutely, there is gas, but the gas is very low density, tenuous compared to the amount of gas that's required to form these stars. So presumably there was some gas that came in from the outside. There was some fueling of the center of the galaxy.
So let's maybe talk about some of the other surprises that you.
The old stars. Where are the old stars?
Well, yeah. Even though there are young stars, shouldn't there still be some old stars?
Well, we would anticipate there is lots of old stars. And in fact, that idea is how we find, in many cases, black holes at the center of other galaxies. We look for this intense concentration of light from the old stars, and yet we're not seeing that in the case of our own galaxy, where it's very clear that there's a black hole. Today, this is still it's still a mystery. We don't understand this. This is part of what we're trying to do this run, is understand what might be happening. And the key here, at least for our approach to this, is to understand the orbits. Because the old stars are somewhat further out from the young stars, this just requires more dedication. And so this is what we're doing tonight. Tonight we have the two telescopes, so this animation shows nicely what you would see if you were on the top of Mauna Kea, the two lasers pointing at the center of the galaxy, because we're fortunate enough to have two. We can talk about G2. Okay, so there's
G2. So we're talking about gas and new stars forming and everything. And then there's one of this unusual object known as G2. What is G2?
Well, G2 is an object that was posited to be a gas cloud. In fact, maybe we can show the animation of what people had anticipated. This is an object that's seen only at very long wavelength emissions. So all the images that we've been showing you so far, and that Brianne is collecting for us tonight, are at 2 microns, at a wavelength of 2 microns. This is an object that you can't even see at 2 microns. But if you...
This one?
It's this one. if you go to 3 microns, you can see this object. So it's visible and quite bright at long wavelengths. And then if you look spectroscopically, you can see emission from a hydrogen emission line. And people said, well, maybe this is a gas cloud that's infalling towards the black hole, and that the black hole is going to tidally disrupt this object. The idea of tidal disruption came from observations of the gas line, which showed a stretching out of the object as it got closer.
So this animation is a model of what might happen if a gas cloud became drifted close to the center of the galaxy. And so is this what is in fact happening then?
Well, this is what, we call this the year of G2. In fact, this animation was done when the object was first found, and it was anticipated that the closest approach for this object should have happened last year. We actually now understand that the closest approach is happening this year. And so the big question was, is G2 going to completely fall apart and feed the black hole? So one of the things that we're really interested in seeing on the other side, the other telescope, is whether or not we still see the object. We did an experiment last night where we showed that at 3 microns, it's still there, which really argues against the idea that this is a pure gas cloud, and that there must be something at the core holding the object together. Now, Brienne has also told us that tonight we're seeing very little emission from the black hole. It's very faint and very quiet, which again is inconsistent with this idea that there's a gas cloud that's fueling the black hole. So it's likely not a gas cloud? Is that sort of the way the data are starting to indicate? I think it's not a simple gas cloud. So the idea that it's a pure gas cloud and it's going to completely fall apart and be fed into the black hole is incorrect. There's clearly gas associated with the object, but I think what we're quite convinced of today is that there's a central star. Now this has got to be an unusual star for this thing to be big enough to have tidal effects, for the black hole to be able to affect it at the distances that it is today. Today we think it's a roughly 200 astronomical units based on the orbit. That's about twice the size of the solar system. For the black hole to have any influence on this object, it has to be incredibly big. So it is an unusual star, although I think we're quite convinced today that it is a star.
So you mentioned that on the Keck 1 telescope, the other telescope, right now we're in the control room for Keck 2, but they're studying G2. Why don't we go over and see what's happening over there? And we're going to try and go mobile here with our video stream. We could maybe just switch to this one and just go with the laptop. Okay. So changing live, and then so the two control rooms are adjacent to each other in our headquarters here. So it's just a short walk. If we were at the summit, so okay, we're going mobile. I'll try to be steady. If we were at the summit, the walk from one telescope to the other would be a little longer, would be 80 meters. But we've got other scientists that are part of the team here. That's Eric Becklin. You want to say hi, Eric?
Hi.
Eric's long been studying the Galactic Center and one of the pioneers of infrared astronomy and still a key member of the team. So now we're moving into the Keck 1 control room. Hi everybody, you're live on video stream out going with the World Wide Web. So Andrea, you want to introduce some other members of your team here?
Sure. So here on the other side, we have 2 more grad students. Anna Bailey, who's here controlling OSIRIS, which is our spectrometer, and Sam Chappell, who's a first-year graduate student at UCLA. So this is Sam's first time at Keck.
Hi, Sam. What do you think? How do you like Keck? Yeah. Hi, Anna. So you're observing the Galactic Center right now with the spectrometer OSIRIS.
Yes.
And what are you seeing?
Well, we're looking for a tick-toed star, and we have some, and then after that we're going to offset to our
Well, you're a good sport for letting us invade your observations here. So the OSIRIS spectrometer gives you some different information about what's going on. Like why is G2 more? Why are you trying to study the G2 star with OSIRIS?
Well, with OSIRIS, we see the gas, the hydrogen emission line. So we see the gas with OSIRIS. It's a spectrometer, so we can actually detect the gas.
Spectroscopic features that show up
features.
that are signatures of excited gas.
Exactly.
Yeah, okay.
And then with the images, we're actually seeing the dust. So we're actually tracing very different things. And we actually are seeing different things. With OSIRIS, we're seeing that the object is much harder to detect this year than it was last year. In contrast to the dust, in which case it's absolutely the same as what we saw last year. So there's different. We're tracing different phenomena.
I see. Yeah, fascinating. So on G2, we'll have to stay tuned to find out what this enigmatic object actually is.
It's keeping us all entertained.
Yeah. All right. Well, thank you guys for letting us come over to Keck 1. So we're going to walk back to Keck 2 now, and then start considering signing off here. So yeah, we're at the Keck headquarters in Waimea, on the Big Island of Hawaii,
In the image?
and we're doing a live video stream into an observing run where we're studying the environment around the center of our Milky Way galaxy, which includes a supermassive black hole, and as we've heard, lots of other interesting objects and a lot of things going on there. Very dynamic place. It's interesting to me. You think in astronomical time scales. Usually, we're talking, as you mentioned, star formation takes millions of years, and old stars live as billions of years. But in just a few years, you're able to see complete orbits of these stars around this black hole, and it always amazes me that so much is happening on a human time scale, not an astronomical time scale, and it makes it one of the more fun. If you're a short attention span astronomer, it's an
Things happen.
ideal project for
We
you.
definitely come back each year and
Yeah.
really excited to see what's up with the stars in the center of the galaxy.
And there's a lot to look forward to because you've got SO2 closest approach in 2018, and a test of general relativity, and a lot of things happening there. What's going to happen to G2? You're getting orbits of some of these young stars further out to try and understand where they came from. And so much to look forward to.
We're having a great time. There's so much to be learned,
Yeah.
and the technology just makes it better and better every year. So we're very fortunate to be able to work at Keck Observatory.
Okay, well, on that note, I will, I guess, go ahead and sign off. And this is, again, my name is Randy Campbell. I'm a staff member here at Keck Observatory, and it's been my pleasure to host this live video stream tonight. And I hope you found it interesting. Thank you very much for joining us.